Okay, guys, the next chapter that we're going to talk about is heat and work. Sorry, it's this video is about heat and work. The next topic that we're going to study in AP Chemistry, though, is thermochemistry. So thermochemistry deals with how energy gets transferred, especially in the form of heat during chemical reactions. So we're going to talk, we're going to look at that. We're going to look at heat very specifically. But before we get into that, we have to kind of back up a little bit and look at the more fundamental physics of that. So that's what this video is about. It's going to be focusing on these two quantities of heat and work and how they relate to something called internal energy. So when we talk about heat and work and how they relate to energy, we have to look at the first law of thermodynamics. So when we think about energy, there's this idea that the energy content of the universe is constant, or for any process, energy has to be conserved. But that's only for a closed system. That's only if we don't allow energy to flow into or out of the system. But obviously, we can add energy to it, or we can take energy away from it. Our car engines, output energy, and we use that to move, the car. So when we think about like changes of energy, we have this quantity called internal energy, and very often this is abbreviated with a U. I might do that accidentally, so just be aware of that, but let's call that delta E. So this is going to be the change in internal energy of the system, so kind of the energy content of the system. So change of in internal energy, okay? So change in internal energy. And what the first law of thermodynamics says is that the only way to change the internal energy of this system is through heat. So we use Q to represent heat, and that's measured in joules, or work. Okay, so this W stands for work, which is also, we measure in joules, and so this change in internal energy will be in joules as well. So what this is saying is that if we have a system, it's going to have a certain amount of internal energy. But if we allow heat to flow into or out of the system, or if we get work out of the system, or we do work on the system, then that's going to change the internal energy of it. Okay, now a little bit about sign conventions, because again, heat can flow into a system or can flow out of the system. Same thing with work. So the sign conventions that we use in chemistry are, positive Q. What that means is that heat is added to our system. Okay, added to our system. And very often the system we have in chemistry is our chemical reaction. Negative Q, so Q will be negative when heat is released, okay, or exits the system. Okay, so if heat's leaving our system, we'll have a negative heat flow. If heat's added to our system, we have a positive heat flow. So be very careful with these sign conventions. Work is very similar. So positive work is when work is done on our system. Okay, so we don't run across work quite as much in chemistry, but we'll talk about one case in which we do think about work in chemistry. So if we do work on our system, we add energy to it, and so it's going to be positive work. The negative work is if work is done by our system. That's work done by our system. So if work leaves our system, okay, we use some of the energy in the system to do work on something else, that's going to be a negative workflow, and it's going to lower the internal energy of our system. Okay, so this, let me use a different color here because I can. This, okay, right here is the first law of thermodynamics. Okay, anyway, I don't break that, but that's the first law of thermodynamics. So that tells you how you can change the energy content of the system by doing work or exchanging heat with the system and the surroundings. Okay, so with that in mind, let's kind of focus on each one of these quantities. We're going to start with heat. So as we said, heat is the energy that's transferred between objects at different temperatures. Okay, so heat is not temperature. Heat is, it's a form of infrared radiation. It gets exchanged between objects. So if I have object A, I can exchange heat to object B. Okay. But this heat is the energy that gets transferred. Okay, it's not the temperature. So the thing is, we don't really have any way to measure heat. We don't have a device like a thermometer that can measure heat. We do have a device that can measure temperature, though. And so what we do is we say, okay, we know if heat flows, like say to our system, if we add heat to our system, we know it's going to change the temperature. So we know, I'm going to erase this equal sign here. So we know that this heat is proportional to the change in temperature. Okay, however, we want an equality here. And we know that the more stuff we have, the less the temperature is going to change. We also know that some substances can absorb heat and change temperature by a lot, where other substances absorb heat and change temperatures by a little. And we come up with this equation. So I'm just going to show you the equation. Q is equal to mc delta T. So this is how we get our equality. This m is our mass, so the mass of the stuff. Q, as I said, is our heat. This is our change in temperature. Unlike gases, it doesn't matter what units you use for this temperature. You just want to be consistent with this. Right here is called the specific heat capacity. Okay, so the specific heat capacity, and that's going to have units. Usually, it's going to be grams per. Sorry, got it upside down. It's going to be joules per gram degrees Celsius or degree Kelvin. A change of 1 Kelvin and a change of 1 degree Celsius is pretty much the same change. So if you have a joule per gram Kelvin, it's going to be the same number. All right, so let's look at this specific heat capacity a little bit more. Okay, and let's look at these units. So say that something has a high C, a high specific heat capacity. What that's saying, if you look at the units here, joules per gram degree Celsius, so what that's saying is that a lot of heat needs to be exchanged. So either flows in or flows out, needs to be exchanged in order to change the temperature. Okay, so a high heat capacity, now if you look back at this equation here, if C is high, then Q will have to be higher in order to achieve any given change in temperature. Whereas, the opposite is true. If we have a low C, a low heat capacity, then little heat is needed. Little heat needs to be exchanged to change temperature. Change temperature. Okay, so let's see what other should we have? Oh, here's an obvious example. Okay, if we have a piece of copper, a piece of copper. Copper has a low heat capacity. So if I add some heat to it, it's going to change its temperature by quite a bit. If I add the same amount of heat to water, water has a high heat capacity. So add the same amount of heat to copper and to water. Copper is going to change the temperature a lot because, Q equals mc delta T. They have same mass of copper and water. If C is lower for copper, then the change in temperature will be higher for any given addition of heat. Okay, so that's going to be a conceptual question. You're going to be asked to compare different objects and told like the difference in heat capacity, and you may be asked to predict like which one undergoes a higher change in temperature. Okay, and so you base that on the specific heat capacity of the two substances. All right, so if we have two objects and they're in thermal contact with each other, okay, so say maybe we drop a hot piece of iron in a beaker of water, then we know that the heat's going to be exchanged to the water. Okay, so say that the iron is at, 87 degrees Celsius, and then you have water, maybe at 22 degrees Celsius. Okay, we know heat's going to be exchanged. And what we kind of want to do is we want to find out, well, okay, fine, but what's the temperature going to be? Okay, and one of the conservation of energy things is that the heat lost by, say, this iron has to be equal to negative heat gained by the water. Okay, so however much heat the iron loses, water has to gain that much heat. I'm going to change this negative sign. Okay, so just be consistent because heat lost is negative, right? So take the negative of the negative. That gives us a positive for the heat gained. So this comes from the conservation of energy. Okay, heat loss is equal to heat gain. Now, as I said, we can't measure heat. So what we could do, though, is instead of saying Q, we can express Q in terms of mc delta T. So what we would say is negative, maybe mass of iron times specific heat of iron is equal to final temperature minus initial temperature for iron. And that's got to be equal to the mass of the water times specific heat of water times, again, final temperature minus initial temperature for the water. And what's going to happen with problems like this is that they have to have the same final temperature. If they don't have the same final temperature, then heat will flow back and forth until they do. So they'll start with different initial temperatures, okay, but they'll have the same final temperature. And so you can use this idea to solve for what the final temperature will be if two objects at different temperatures come in thermal contact, which means heat can flow between them. You can use this idea, you can use mc delta T, and you can solve for the final temperature of those two objects. Okay, so we talked about heat a little bit. The other part of this first law is work. Now, in chemistry, as I said, we don't really deal with work too much, but one way in which we did do it is with gases. Okay, so we have a cylinder. If we have a cylinder, okay, and we have a piston in the cylinder, and this piston can move up and down. Okay, we have our little gas particles in here. Okay, if that cylinder moves up or down, there's going to be a change in volume that occurs. Okay, and I'm gonna, you guys should have read your textbook for this derivation, but the work done in this process, okay, so we're gonna have a constant pressure this whole time, okay, and the work done in this process we say is negative P delta V, okay, so the work done in joules is going to be equal to the pressure that the process occurs at times this change in volume, which is final volume minus initial volume. Okay, and this is called PV work. So if we have a reduction in volume, okay, so if VF is smaller than VI, then this will be a negative change, but we have a negative here, and this negative here is to make sure we're consistent with our signs. So because if we do work on this, we'll compress that piston, and that's going to be positive work. Okay, it's going to be positive work. And then again, this is going to be done at, we'll only consider the case at constant pressure. Okay, so this is the PV work. So, you have this idea that if you know the change in volume and you know the pressure which it occurs at, you can calculate the work done. And if you know the heat that was exchanged, you could use the first law once again. Q, is equal to, let's say this, Q is equal to negative P times delta V. Okay, you could actually plug that in and you can figure out how much heat was exchanged that way as well. Okay, so this is a very special type of work. It's PV work. Okay, it's pretty much the only type of work though that we'll be dealing with in here. And again, if you want to see a derivation of that, feel free to look in your textbook, and they run it through you from the definition of work, which is force over distance, all the way to right there. All right, so those are the concepts. In class, we'll practice, problem solving with this, and some conceptual exercises and how we can apply this to different situations. If you guys have any questions, please let me know.